Hi! Today we are gonna talk about horsepower and torque, where they come from, what they do, and most importantly, which is better for your engine. I'll keep it simple without any complicated formulas, and also I'll try to communicate the whole topic in respect to the internal combustion engine, not just some abstract power and abstract torque. It'll be about engine power and engine torque. Let's go! Before we start arguing about what we need more, that beefy low-end diesel tractor torque or that puny mosquito sounding high pitch of 1 horsepower, let's step back for a minute and look at what actually makes our vehicle go. What is really important in a fundamental way. On our roads, we have all sorts of cars, trucks, motorcycles, ATVs, all sorts of vehicles. And they all have different engines, gearboxes, transmissions, etc. But at the end of the day, what makes them all go forward is the friction force between the wheel and the road. If you, for example, lift the wheel from the ground, it's quite obvious that your car won't go anywhere, regardless of how powerful its engine is. So, what we are really ultimately aiming at is this friction force between the tire and pavement, which propels us forward. This force is limited by coefficient of friction between our tire and the road. We can't really go beyond it. If we try to, our tire just starts to slip and we don't really accelerate any faster. Now, when we discuss engines and its properties, torque and horsepower, performance-wise, what we really wanted to do is to be able at any given moment achieve this maximum force on tires for best possible acceleration. And what creates this force? That's where we have to meet the torque. Usually, when people explain torque, they demonstrate something like this. Let's say we have a nut and a spanner, and we apply some force to make the nut tight. If we want to make the nut tighter, we can either increase the force on the spanner, or we can increase the length of the spanner itself. Both of these actions will produce more of the twisting force on the nut and make it tighter. This twisting force is called torque. In this case, twisting force, or torque, on the nut is produced by applying a force through the leverage of the spanner. Torque is a byproduct of force and a lever. But it can also be the other way around. Let's say that we have a long nut, so we can put one more spanner on it. Now, the torque on the nut, created by force and leverage from the first spanner, can create a linear force on the second spanner. And this force can be used to move other objects. That's precisely what happens with our wheel. Torque produced by our engine goes on our wheel through the transmission and finally through the wheel itself ends up transformed into the linear friction force, which pushes against the road surface and propels us forward. So, if it's the torque which ends up as a force accelerating us, then the torque is the way to go. It's all that matters, right? No, it's not right, and here is why. Let's turn to our example with spanners for a second. As we see, the torque on the nut doesn't just appear spontaneously. It is a product of a force acting through the lever. And that's true for our internal combustion engine too. Torque doesn't just being produced magically by the engine. No, it gets a while to produce this torque. At first, piston in the cylinder goes down and sucks the fuel and air mixture in the cylinder through the intake valves. Then, valve closes and piston goes up, compressing the mixture. And only then the mixture goes kaboom and pushes the piston down again. And that's not the end. After that, we have to open the exhaust valves and push the exhaust gas out. As you can see, torque on the crank of the engine is created by the force of the expanding gas acting through the piston and the con rod. And this torque is created not continuously all the time, but only during the combustion cycle, once in 4 cycles, or every 2 rotations of the crank. This means that we have to consider not only the torque, but also the engine RPM. If we have more RPM, it means the torque is created more times in our cylinder for any given time period. Both Torque and RPM are important, and torque and RPM combined gives us the horsepower of the engine. Horsepower is simply torque times RPM. You even can check it yourself. Find any power and torque diagram for any engine you want. Now, pick any RPM you want and multiply it by the torque value for that RPM. Then you divide it by 5252 and voila! You have your horsepower. We have to divide it by 5252 just because we traditionally measure power in horsepower, torque in foot-pounds and engine crank angular velocity in RPM. If we would use standard units and measure torque in Newton meters and measure angular velocity in radians per second, we could directly multiply torque and angular velocity and get power in watts. But that's not really important. Important thing is that engine power is simply its torque multiplied by RPM. So, what does really matter at the end? Torque and RPM is what matters, and power is simply torque times RPM. At the same time, by definition, power is the amount of work your engine can do for a given period of time. Here is the analogy. Imagine that you are playing football and you need to kick the ball through the entire field, 100 meters. You can do it by kicking the ball really hard couple of times, or you can kick it 10 times with less force, achieving the same result in the end. In this analogy, how hard you kick the ball each time is your torque, and your RPM is how frequently you do it. The 100 meters is your work, which needs to be done, and kicks times their frequency, torque times RPM, is your power. The harder you kick the ball and more frequently you do it, the faster you run your 100 meters and do your work. Therefore, the more power you have. This analogy is not too far off from our situation. In a sense, each combustion cycle in our cylinder goes through the whole transmission to our wheel and gives us a little kick forward. And with more RPM, we have more of these kicks per minute. And the higher the torque and more the RPM, the more distance we can go in a shorter period of time. That's our horsepower, torque times RPM. Now wait a minute, something smells fishy. More horsepower means more distance for a shorter period of time, right? I just said it myself. So, why all this torque and RPM nonsense when we can just look for more power and that's it? Two reasons. First, I just wanted to emphasize where the power comes from. Power depends on how frequently the fuel in your engine goes boom and how strong each of these booms are. Power is a product of torque and RPM, it's not a separate entity. And second thing, the horsepower value which the manufacturers gives us can be a bit misleading. What we can usually see in our vehicle description is a peak horsepower value, the highest possible power your engine can produce. And the problem is that it happens only on certain RPM. And of course, we can't use our engine on only one RPM. It's obvious that we need to know how it performs through the whole range. That is precisely why we use torque RPM diagrams, where we can see torque and horsepower in relation to every possible RPM the particular engine has. As you can see, on different RPM, torque can be significantly different. That happens because on different RPM the engine piston obviously has different speed. The higher the RPM, the faster the piston has to move. That in turn means that at different RPM, the air-fuel mixture gets sucked into the cylinder at different speed too. And since we deal with real air, real gas, which has its own mass and inertia, on different speeds it can behave a little different. On some RPM it fills the cylinder nearly perfect, and on other RPM it does not due to different pressure wave and turbulence effects. On RPM, where the mixture fills the whole cylinder good and even, the fuel burns well and we have a good torque. And on some RPM we have a poor torque, because there is less fuel in the cylinder or it is distributed unevenly and can't burn completely. RPM where engine performs good can be seen on the diagram as peaks of torque. and where it performs bad as dips. Those RPM ranges depend heavily on the particular engine design features, such as bore-to-stroke ratio, head geometry, how many valves it has, and other stuff like that. And also, where engine performs well can be tuned by some components, for example, with different cams, different airboxes or exhausts. Engines that are made to perform well in higher range are usually considered as revy or power engines. And torquey engines obviously perform better towards the middle range. For pure performance needs like racing, we always go with revy engines. As an example, let's look at Yamaha R1 engine. That's as much performance as you can possibly buy from a factory. As you can see here, we have rather poor performance up to 8500, and then we suddenly have massive torque up to the highest RPM. Big torque times high RPM results in huge horsepower. 160 horsepower on rear wheel from a liter engine. Pretty impressive if you ask me. But that's for a performance, for racing. For everyday riding, this engine probably will not be the greatest choice, since you rarely need to go to 180 miles per hour and jump from 0 to 60 in 3 seconds. And you probably don't want to constantly rev it above 8500, right? That's why for civil use we have more torquey engines. Let's look for example at Ducati 1200 Monster engine. It's still pretty advanced and high-performance bike, but it's intended not for racing, but for more everyday riding. Look how different the engine performance is. We have good torque from around 4500 up to 9000. Remember how on R1 torque just started from 8500. And here 10,000 is pretty much as high as we can go. So this engine has much higher torque than previous one. But the RPM are much lower, so it has much less power as the result. That means you won't have the top speed that you would have on R1, and you'll accelerate slower on higher speeds. But on lower speeds you even may have an advantage, because on lower RPM you have higher torque, and therefore on those lower RPM you also have more horsepower. You have more horsepower until the revy engine gained its RPM. But what's more important, those torquey engines are simply more suited to day-to-day life. They have better gas mileage because you use them in RPM range, where the combustion is most effective. And you don't need to become deaf because you have to rev the shit out of it. And at last, let's look at the example of extremely low torque engine. Harley or Holy American V8. Of course Harley, we are bikers here. But for V8 it will be pretty much the same line of thought. Here is 114 Harley engine dyno chart. Look at this ridiculous torque at the very low range. The torque is freaking huge. But at the same time, the RPM of this engine is pretty low. 5500 is as fast as it gets. So the power, despite the huge displacement and insane torque numbers, is pretty modest. From the performance view, this makes no sense. You really don't need that much torque at low end, because remember from the beginning of the video, if you give too much torque to the rear wheel, it just starts to slide and don't really do much acceleration. For on-road use, unless you really want to do burnouts or tow something really heavy, this huge low-end torque is kind of useless. And on higher speeds, when we start to need power to overcome the wind resistance, the engine can't give it, because it can't spin fast enough. Because of that, from performance standpoint, those engines are not very good. But cruisers, and especially Harleys, are a pretty interesting phenomenon. They are not just the means of transportation. They are, in a sense, cultural thing as well. Nobody seriously buys them for performance or gas mileage or other practical stuff. And those engines are pretty cool for that particular reason. They let you ride on very low RPM, which produces specific sound and feel to the bike. They let you ride on almost any gear, and if you keep them stuck and service them as intended, they will pretty much last forever. for practical reasons, those engines are ancient crap, but they're pretty cool at the same time. Some people like it and some don't. And old V8s are pretty much the same deal, only for cars. So, just in case, don't fall for this low torque is king stuff. It's a lie. You need both good RPM range and good torque curve, not just peak power or peak torque numbers. Alright, that video was a bit experimental. Write me at the comments if you'd like to see more of this, or you like the riding videos better. And put a thumbs up or down. And don't forget to subscribe to the channel, I appreciate it very much. Thank you for watching, hope to see you soon. Bye.